Mid-February 1943, Sidi Bouzid, Mamoun Ahmad. Mid-February 1943, Sidi Bouzid, Tunisia. The captured M4A1 Sherman tank came to a halt in the desert sands, its American star still faintly visible beneath the hastily brushed-on German cross. Officers from Heavy Panzer Battalion 501 assembled around this trophy, notebooks already open. This single American tank, seized intact and fully functional during the Battle of Sidboid, would spark a crisis of confidence among German engineers that resonated throughout their tank development. Efforts for the remainder of the war, the mathematics of armored warfare, were about to be redefined, not through superior guns or thicker armor, but through something the Germans had never emphasized: automotive reliability that simply refused to fail. The tank bore the name War Daddy 2 stenciled on its hull. Serial number USA 30676441, manufactured by Lima Locomotive Works, and assigned to Company G, 1st Armored Regiment. 1st Armored Division. Personnel from a German reconnaissance unit drove this Sherman over 350 kilometers across North African terrain to the port of Sfax, a journey lasting 4.5 days. Every kilometer revealed something that challenged German beliefs about American industrial capability. The engine never overheated. The transmission never faltered. The final drives delivered consistent performance. German crews, accustomed to frequent mechanical breakdowns even on short marches, watched with growing unease as this enemy machine functioned flawlessly across terrain and conditions that would have crippled their own equipment. At the port, War Daddy 2 was loaded onto a cargo ship bound for Germany. The Army Weapons Office had issued strict orders. The tank must arrive at the Kummersdorf testing facility intact and operational. German intelligence had gathered fragmented reports on American tank production, but seeing the vehicle itself gave those numbers meaning no paper report could convey. The Sherman embodied mass production on a scale Germany could not rival. Built on automotive engineering principles it had never mastered. As the ship steamed north across the Mediterranean, Wehrmacht engineers prepared test protocols that would expose truths they had long avoided about their own limitations and America's strengths. Spring 1943, Kummersdorf Proving Ground, Brandenburg, Germany. War Daddy 2 rolled off the transport rail car bearing the marking Zugkraft 259 and the German license plate, EUCH 058941. Test engineers had already stenciled armor thickness measurements and angles over every surface, marking it for their exhaustive evaluation program. The Kummersdorf Proving Ground, located 25 kilometers south of Berlin, served as the principal testing site for both German and captured Allied equipment. Here, meticulous engineers measured, tested, and analyzed everything, from track tension to transmission efficiency, recording their results in detailed technical reports. The Sherman was about to undergo the most thorough automotive examination German engineering could produce. German test teams began with specialists from multiple technical branches. They photographed every component from dozens of angles, measured each clearance with precision instruments, and documented construction techniques that appeared almost deceptively simple compared to German methods. The transmission immediately drew the attention of powertrain experts. Where German tanks used straight-cut gears demanding exact tolerances and constant maintenance, the Sherman employed herringbone-cut gears that spread stress across multiple teeth at once. This design, standard in American automotive manufacturing since the 1930s, offered exceptional durability with minimal precision requirements. German engineers had long dismissed herringbone gears as too complex to mass-produce, given their industrial constraints, yet the Americans had been turning them out by the thousands. Testing began with basic automotive trials designed to strain every mechanical system under controlled conditions. Engineers drove War Daddy 2 through obstacle courses replicating battlefield terrain, measuring fuel consumption, monitoring engine heat and recording transmission behavior under varying loads. After each run, components were disassembled to study wear patterns, searching for stress marks, lubrication issues, or design flaws. The results overturned everything German doctrine assumed about performance versus reliability. The Sherman performed respectably in every category and excelled in the one area German tanks habitually failed: operational endurance without constant maintenance. The powertrain analysis revealed the contrasting philosophies behind American and German design. The Sherman's transmission had 5 forward gears and 1 reverse, with synchronization from 2nd through 5th, eliminating the need for double clutching. It made the tank almost as easy to drive as a civilian vehicle, requiring only basic training. German tankers, by contrast, spent long hours mastering intricate double clutch techniques and careful throttle control to prevent transmission damage. The Sherman's design assumed that ordinary soldiers with modest mechanical skill would operate these machines, while German designs relied on highly trained specialists. Its Continental R975 radial engine showed impressive tolerance for varied conditions, maintaining stable performance across temperatures that would cause German engines to overheat or lose power. The cooling system, though simple, proved highly efficient. The air filter managed desert dust, without the frequent clogging that had plagued German tanks in North Africa. Every component reflected a philosophy of practical functionality, rather than theoretical perfection. June 6th and 7th. 1943, Hillersleben Artillery Range. Reichsminister Albert Schaar arrived to preside over a major armament conference attended by leaders from the armaments industry and senior Wehrmacht officers. The demonstration program included hill-climbing trials comparing German and captured Allied tanks. War Daddy 2 sat alongside the latest German designs, including a Panther AKF DM tank fresh from production and a Ferdinand tank destroyer representing Germany's most advanced armored fighting vehicle technology. Schaar, responsible for German armaments production and personally accountable to Hitler for results, needed to understand what American industry could produce and how German designs measured against enemy equipment. The demonstration would provide answers neither Schaar nor German tank designers wanted to acknowledge. The Sherman climbed the test slope smoothly, its manual transmission with 5 forward gears, synchronized from 2nd through 5th, shifting without hesitation, its engine maintaining consistent power delivery throughout the ascent. The driver handled the vehicle with confidence, demonstrating the ease of operation that would become a Sherman hallmark. The Panther followed its more powerful 700-horsepower Maybach HL-203 engine, allowing it to match the Sherman's performance, but only barely, and with considerably more difficulty. The Ferdinand, massively heavy at 65 tons and technically sophisticated with its electric transmission system, stalled partway up the incline. Speer watched as recovery crews struggled to restart the vehicle, the embarrassing failure occurring before dozens of senior officers and industrial leaders. In his memoirs years later, Speer would write about Sherman capabilities he observed during his inspection tour of Italy in October 1944. He noted that reports on the cross-country mobility of the Sherman had been very favorable with the tank. Climbing mountains German tank experts considered inaccessible to tanks. He attributed this to the Sherman having a very powerful motor in proportion to its weight, giving it cross-country mobility on level ground that was definitely superior to German tanks. The 26th Panzer Division had specifically reported this advantage. These observations from Germany's armaments minister carried significant weight within Wehrmacht circles. The written public assessment appeared in Das Reich newspaper on June 27, 1943. The article described the Sherman as one of the special accomplishments of the North American laboratories and called it quite a praiseworthy product of the North American steel industry. The article noted that the first things to attract attention were serial construction and fulfillment of the almost arrogant requirements of the North American automobile industry. The piece mentioned the gyro-stabilized Gunas, the first attempt of its kind ever to be made anywhere, acknowledging American innovation in this area. These public statements, carefully worded for propaganda purposes to avoid appearing defaced, nevertheless concealed the private alarms spreading through German engineering departments. American tanks weren't just adequate. They were fundamentally better engineered for sustained field operations. Back at Kumdorf, systematic testing continued through the summer and into autumn of 1943. Engineers measured the Sherman's operational range, conducting extended trials that pushed the vehicle to its limits. They documented operational ranges exceeding 2,000 km before requiring major maintenance, roughly 4 times what early-model Panthers could achieve in field conditions. They measured transmission efficiency that exceeded any German tank with power losses through the drivetrain significantly lower than comparable German systems. They examined the synchronized manual transmission that made gear changing smooth and simple, requiring neither the double clutching nor the careful rev matching that German transmissions demanded. The final drives presented another revelation that challenged German engineering assumptions. German Panther tanks employed final drive systems inherited from the Tiger design, a configuration prone to failure under stress. The design used straight-cut gears and housings that proved inadequate for the loads imposed by the 45-ton vehicle. German mechanics in North Africa and on the Eastern Front had reported final drive breakdowns, forcing Panthers to be abandoned after relatively short movements. Sometimes less than 100 km, the Sherman's final drives, built using the same herringbone gear principles as the transmission, rarely failed, even under sustained combat conditions that would destroy German components. Restoration projects decades later would find Sherman final drives that needed no mechanical restoration after years of storage. Testament to design margins that exceeded immediate requirements by substantial factors. By late 1943, Kumdorf had accumulated enough data to produce comprehensive internal reports that circulated through Wehrmacht technical branches. These documents, intended for senior Wehrmacht officers and armaments ministry officials, painted a sobering picture of comparative capabilities. The Sherman demonstrated American automotive engineering maturity that Germany fundamentally lacked despite its theoretical knowledge and scientific expertise. Mass production techniques allowed tolerances that would be considered sloppy in German precision manufacturing, yet resulted in more reliable vehicles that functioned better under field conditions. Interchangeable parts meant field repairs could be accomplished with basic tools and minimal specialized training. While German vehicles required factory-level precision and specialized equipment for many repairs, the entire design philosophy prioritized keeping vehicles operational rather than achieving theoretical performance maximums that looked impressive in specifications but couldn't be maintained in combat. Internal German engineering assessments documented observations about American industrial advantages that went beyond simple production numbers. American automotive engineering reflected decades of civilian industry experience that Germany had never developed at comparable scale. Before the war, the United States had widespread automobile ownership, with vehicles commonplace among ordinary citizens across all economic classes. Germany had far more limited civilian automotive experience, with cars remaining luxury items for the wealthy and party elite. The Volkswagen program promised to German workers since 1934 had delivered fewer than 1,000 civilian vehicles by 1939. This vast difference in automotive industry maturity translated directly into tank design philosophy. Americans built tanks that mechanics with civilian automotive training could maintain using skills they already possessed. Germans built tanks that required specialist training and constant expert attention from personnel with years of specific military technical education. The comparison with German tank reliability became impossible to ignore as field reports accumulated through late 1943 and early 1944 Panther. Tanks required strict operational restrictions to prevent mechanical failures that would leave them stranded. Drivers received explicit instructions not to change gears frequently, as excessive shifting damaged the transmission. Third gear, in particular, broke often enough that field manuals warned against its use, except when absolutely necessary. Panthers could not turn while backing up, as this would destroy the transmission. Pivot turns were only possible when ground resistance was equal on both tracks, severely limiting tactical flexibility. Foreign objects entering the running gear could jam the drive sprocket, requiring hours of maintenance to clear. These problems existed despite Panthers being built in dedicated tank factories by skilled workers using the best available materials Germany could provide. The Sherman, by contrast, had been designed by automotive engineers at General Motors, Ford, and Chrysler, applying mass production principles they had developed over decades of civilian vehicle manufacturing. The tank incorporated commercial automotive components wherever possible, leveraging existing supply chains and manufacturing expertise. The transmission came from multiple manufacturers, including Caterpillar Tractor, Buick, and Ford Motor Company, all building to identical specifications with fully interchangeable parts that could be mixed freely without adjustment. This standardization, routine in American automotive industry, remained largely theoretical in German tank production, where each manufacturer introduced subtle variations that prevented true parts interchangeability. Additional captured Shermans arrived at Kumdorf through 1943 and 1944, including tanks taken from British units in Italy and Soviet forces on the Eastern Front. Each captured vehicle underwent similar testing protocols, building a comprehensive database of American tank capabilities across different variants and production periods. The British had refitted some Shermans with their 17-pounder anti-tank gun, creating the Firefly variant that addressed the Sherman's main weakness in firepower. German engineers examined these modified tanks with particular interest, noting how the Sherman's large turret ring accommodated the significantly larger gun with minimal modification. The Firefly demonstrated growth potential built into the original design that German engineers had not considered when specifying their vehicles. The Panther, rushed into production to counter Soviet T-34 tanks, had no capacity for significant armament upgrades without complete turret and vehicle redesign. The automotive testing program expanded to include reliability trials specifically designed to replicate combat conditions. Engineers drove Shermans through hundreds of kilometers of cross-country movement, recording every mechanical incident, maintenance requirement, and component failure. They compared these results with field reports from Panther and Tiger units operating on the Eastern and Italian fronts. The numbers told an unambiguous story about comparative reliability. Panther operational readiness averaged below 40% through most of 1943, with some units reporting catastrophic rates as low as 20 to 25%. Individual Panther battalions documented periods when fewer than 1 in 5 tanks were actually capable of combat operations. By comparison, Sherman tanks maintained substantially higher operational availability across all theaters. Specific data from German field reports documented Panther reliability problems in devastating detail. In July 1943, during Operation Citadel at Kursk, Panthers achieved only 16% operational readiness, with mechanical failures eliminating more tanks than enemy action. By December 1943, readiness had improved to only 37%. February 1944 reports showed 37% operational. April 1944 reached 50% operational, 50% operational. May 1944 finally achieved 78%. These figures represented the percentage of Panthers that were actually capable of combat operations on any given day, with the remainder broken down awaiting parts or undergoing repairs. The progression showed gradual improvement as design flaws were addressed, but even the best Panther readiness rates never matched what Shermans achieved from initial production. By December 1943, the pattern had become undeniable to any objective observer examining the data. Engine lifespan for the Sherman diesel variant exceeded 3,000 km under proper maintenance. Panther engine lifespan barely reached $1,000 even after improvements addressed the worst early problems. German reports from March 1944 documented that improved Panther engines achieved service life of 700 to 1,000 kilometers, presented as a success. This improvement merely brought Panther engines to roughly 1/3 of Sherman diesel capability. Sherman transmissions required minimal maintenance between overhauls with synchronized gears that made driver error less likely to cause damage. Panther transmissions demanded constant attention and frequent repair, with third-gear failures so common that drivers learned to skip from second to fourth gear to avoid using the problematic ratio. Sherman final drives operated reliably under conditions that routinely destroyed Panther. Final drives within 100 to 200 kilometers of operation, to field reports from German units using captured Shermans, reinforced the Kumdorf testing data with real-world operational experience. German mechanized units desperate for reliable vehicles as their own tank infantry degraded eagerly employed any captured American tanks they could obtain intact. Unlike Soviet T-34 tanks, which Germans modified extensively before use, Shermans entered German service without changes. They didn't require modification because they worked correctly as designed with no fundamental flaws that needed correction. German tank crews who had experienced multiple mechanical failures in their own vehicles found the Sherman's reliability remarkable and frequently commented on it in letters and reports. Reports from panzer regiments noted that Sherman operators could focus on tactical considerations and combat effectiveness, while Panther and Tiger crews constantly worried about reaching the battlefield without breakdown or completing missions before mechanical failure immobilized their vehicles. The 10th SS Panzer Division captured 12 M4A3 Shermans at Hellesheim. In January 1945, during Operation Nordwind, these tanks had belonged to the American 43rd Tank Battalion and were captured intact when their crews abandoned them during the German assault. The 12 Shermans were organized into the 13th Company of the 10th SS Panzer Regiment and participated in combat operations until the war's end. These tanks were used primarily as reconnaissance vehicles and mobile reserves, roles demanding continuous movement, minimal maintenance interruptions, and dependable mechanical performance. German commanders soon recognized what the Kummersdorf testing had proven years earlier. American tanks could be trusted to operate when required. This reliability, more than sheer firepower or armor protection, determined tactical usefulness in the war's final months. A Sherman that reached the battlefield with a functioning gun was worth far more than a Panther boasting superior armament but stranded 20 kilometers behind due to mechanical failure. January 1944 saw expanded testing programs as Wehrmacht forces fell back across multiple fronts, and additional captured vehicles arrived at Kummersdorf. Engineers examined the M4A1 equipped with the Continental R975 radial engine, recording its characteristics and comparing them to other models. They tested the M4A2 with twin General Motors 6046 diesel engines, noting its greater fuel economy and distinctive performance. They also evaluated the M4A3 fitted with the Ford GAA V8 gasoline engine, which American crews regarded as the finest Sherman power plant. Every variant displayed the same core trait: outstanding automotive reliability born from sound engineering and consistent manufacturing standards. The uniform quality across all models impressed German engineers who were accustomed to significant inconsistencies among different manufacturers producing supposedly identical vehicles. The diesel-powered M4A2 particularly impressed those who studied it at Kummersdorf. Soviet forces had received over 4,100 of these tanks through Lend-Lease, and many fell into German hands during retreats on the Eastern Front. The twin GM60046 diesel engine delivered performance comparable to any Sherman model while consuming far less fuel, a critical advantage. As German fuel reserves dwindled, German designers had experimented with diesel engines for tanks but abandoned the idea due to production difficulties and the complexity of fuel injection systems. In contrast, American industry built diesel and gasoline Shermans side by side without disrupting production schedules, demonstrating a manufacturing flexibility and technological sophistication Germany never matched under wartime pressures. By March 1944, reports from General Heinz Guderian, Inspector General of Panzer Troops, noted in official correspondence that improvements to Panther reliability had finally achieved what he called acceptable standards. Engine life had reached 700 to 1,000 kilometers, and final drive issues were largely mitigated through design adjustments and better production methods. Yet this milestone, heralded as a major success in German reports, merely brought Panther reliability up to the level the Sherman had maintained since its first production runs in DTE. 1942, the German Army's celebration of this progress underscored how far behind its armored vehicle development had fallen. The comparison became even more painful as German tank production struggled under growing resource shortages and the intensifying Allied strategic bombing campaign. Allied bombers increasingly targeted key choke points in the Panther and Tiger production chains. The Maybach engine plant in Friedrichshafen suffered devastating damage from a Royal Air Force Bomber Command raid on the night of April 27 to 28. 1944, described in Imperial War Museum archives as the most destructive attack on German tank production during the war. The same raid also destroyed the adjacent ZF gearbox factory, halting engine and transmission output for 6 months. When manufacturing finally resumed in November 1944, quality control had deteriorated badly. Slave labor, increasingly used in tank factories as German workers were drafted into the military, introduced deliberate sabotage. Cigarette filters stuffed into oil passages, gaskets installed incorrectly, and components assembled with improper clearances. Such problems never plagued Sherman production, which took place safely in American factories far from combat and staffed by well-paid, motivated workers under decent conditions. The essential difference between German and American tank production lay not in technical knowledge, but in industrial capacity and design philosophy. German engineers understood automotive principles as well as their American counterparts and possessed deep theoretical and scientific expertise. Yet, they failed to apply those principles consistently to tank design, prioritizing firepower and armor over reliability and ease of maintenance. German tanks emphasized performance specifications that looked impressive on paper, but resulted in poor field dependability. The Panther's powerful 75mm K-42 gun and thick frontal armor came at the expense of an overstressed drivetrain unable to reliably support its 45-ton weight. The Tiger's formidable capabilities required complex maintenance routines and constant attention from highly trained crews. Such trade-offs might have been tolerable if German industry had been able to produce enough vehicles and spare parts to sustain them. But it could not, especially as Allied bombing and raw material shortages worsened. American engineers, seasoned in automotive mass production through decades of civilian industry experience, designed tanks that could be built by the tens of thousands and serviced by mechanics with basic training using familiar tools. The Sherman's powertrain incorporated components proven in commercial vehicles, applying design ideas directly from the automobile and trucking industries. Its electrical system included a backup generator capable of powering the turret traverse even when the main engine was shut down, a feature German designers dismissed as unnecessary luxury, but that proved invaluable in combat. German tank crews could only envy such conveniences, particularly those who had experienced turret traverse failures when engines stalled on inclines. Such features never appeared in German technical specifications because they were never prioritized over armor or gun power. By spring 1944, Wehrmacht units on all fronts were reporting mounting mechanical problems as manufacturing standards collapsed and spare parts grew scarce. Panthers had to be transported by rail for journeys exceeding 100 kilometers, as their final drives could not withstand prolonged road marches. Field commands issued explicit orders limiting Panther movements to preserve the tanks for actual combat, rather than losing them to breakdowns en route. The Berge Panther recovery vehicle, built on the Panther chassis and intended to retrieve disabled Panthers, suffered the same reliability issues as the tanks it was meant to tow. German commanders faced the grim truth that mechanical failures were destroying more tanks than enemy fire, with some units reporting that up to 70% of losses were due to breakdowns rather than combat damage. Meanwhile, Sherman production continued at a pace the Germans could only dream of. American factories turned out 49,324 Shermans during the war, more than the total number of all German tanks of every type combined. British Commonwealth forces received thousands through Lend-Lease, and the Soviet Union obtained over 4,000 diesel variants. Chinese forces imbursed Shermans to devastating effect against Japanese armor that was technologically inferior to both American and German designs. Every theater where Shermans served confirmed what Kummersdorf testing had revealed. Properly maintained Shermans kept running under conditions that would disable or destroy German tanks. German tank crews who captured and used Shermans universally praised their automotive excellence in letters, reports, and post-war interviews. Reports from the Eastern Front noted that German mechanics found even the E-complex Chrysler Appadisatsu multibank engine, with its 5 separate engine blocks, easier to troubleshoot, compared to German tank engines that required specialized knowledge and equipment. The Ford GAA V8, praised by Allied crews for its exceptional reliability and power output, seemed remarkably dependable to German mechanics accustomed to Maybach engines that required constant adjustment of valve clearances, ignition timing, and carburetor settings. The General Motors twin diesel, which the U.S. Army had rejected as less reliable than gasoline engines and relegated to Lend-Lease production, far exceeded the performance and reliability of any diesel engine German industry had produced for tank applications. The Sherman's generous design margins provided another advantage that German engineers came to appreciate. The basic transmission and final drive components originally specified for the 30-ton M4 with 400 horsepower required no major modification to handle the 42-ton M4 A3E2 jumbo assault tank with its significantly increased armor protection. The same components that powered the standard Sherman successfully transmitted 650 horsepower from experimental engines without failure orned for reinforcement. German engineers tended to calculate that such overbuilding represented waste, excess capacity that increased production cost and used scarce materials without immediate benefit. American engineers understood that margins provided growth potential for future upgrades and battlefield reliability that made the extra investment worthwhile over the vehicle's service life. By summer 1944, German tank commanders facing the Allied invasion in Normandy knew their technical disadvantages extended far beyond individual tank capabilities. American artillery superiority, devastating close-air support, and overwhelming logistical capacity combined to overwhelm German forces regardless of tank specifications or tactical prowess. But the Sherman's reliability meant American armored units could sustain continuous operations that German panzer divisions simply could not match. American tank battalions could launch attacks, sustain combat operations, conduct pursuits, and immediately prepare for the next operation without extensive maintenance halts. German panzer divisions had to carefully husband their limited operational vehicles, calculating that every movement consumed precious remaining component life and brought mechanical failure closer. The difference in operational availability determined which force could maintain offensive pressure and which had to carefully ration its limited combat power. German use of captured Shermans in combat operations provided final proof of American automotive superiority from the German perspective. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, attempted to obtain captured American vehicles to disguise their operations. German planners wanted Sherman specifically because of their reputation for reliability. However, the brigade received only 2 Sherman tanks, and only one proved serviceable enough for operations. The serviceable Sherman never actually saw combat due to massive traffic jams that prevented the infiltration operation from achieving its objectives. In an operation requiring vehicles to function without breakdowns while operating behind enemy lines, far from any support, only American equipment offered reasonable chances of success. German tanks, even when fully operational, couldn't guarantee the sustained performance such missions required. January 23, 1945, brought the final official admission of German automotive failure. A meeting of the Panzer Commission produced a report documenting catastrophic final drive failures across all German tank types. The document's findings were devastating. Prior to the 1945 Eastern Offensive, there were 500 defective final drives in the Panzer IV, 370 in the Panther, and only 100 in the Tiger. Additionally, approximately 200 failures had been reported in the Hetze tank destroyer based on the Czech 38 Statuasis. General Wolfgang Thomel, General Lieutenant and Chief of Staff of the Inspector General of Panzer Troops serving under Guderian, explained the operational impact in stark terms. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles and, in some situations, abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. German tanks, built to intimidate through impressive technical specifications, failed in the most fundamental requirement of armored vehicles: mechanical reliability sufficient to reach the battlefield and complete missions. Kummersdorf testing facility prepared for evacuation in early 1945 as Soviet forces advanced relentlessly toward Berlin. Engineers frantically packed testing data and shipped documentation to facilities farther west, hoping to preserve technical intelligence for post-war analysis. Some of the captured tanks, including at least 2 Shermans, were pressed into improvised service with combat units desperately defending the approaches to Berlin. These vehicles fought alongside German designs in the final desperate battles, providing one last comparison under actual combat conditions. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out. The German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even experienced crews accustomed to poor reliability. The story of War Daddy 2 and the dozens of other Shermans tested at Kummersdorf represents one of the great industrial disparities of World War II. German engineers working within an industrial system that prioritized theoretical perfection over practical utility produced tanks that looked impressive on paper but failed in sustained field operations. American engineers applying decades of automotive manufacturing experience to military requirements produced tanks that lacked technical sophistication in many areas but worked reliably under conditions that defeated German equipment. In armored warfare, as in most military operations, the weapon that functions when needed beats the weapon that might be theoretically superior if it could reach the battlefield and complete its mission. Post-war analysis by American and British intelligence organizations confirmed what German testing at Kummersdorf had revealed. Systematic examination of destroyed German tanks found mechanical failures as common as combat damage as causes of loss. Final drives broken from stress, transmissions seized from inadequate lubrication or operator error, engines burned out from overheating or oil starvation. The German obsession with individual vehicle superiority and impressive specifications had blinded them to the critical importance of reliability and maintainability. They built tanks that no conscript mechanic could maintain without extensive specialized training. Powered by engines that demanded constant expert attention from skilled technicians, supported by a logistics system that collapsed under the accumulated strain of supplying countless unique parts to scattered units. The lessons learned through testing at Kumtov directly influenced German tank design thinking in the post-war Bundeswehr of West Germany. When the Federal Republic began developing the Leopard, one main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance. Specifications, they studied American automotive engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 tank incorporated many design philosophies that had made the Sherman successful. Robust powertrain with substantial design margins, easy maintenance requiring minimal specialized tools, standardized components enabling rapid field repairs, and growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The captured Shermans at Kummersdorf, including War Daddy II, with its distinctive name still painted on the hull, represented far more than enemy equipment brought home for technical examination. They were tangible proof that industrial maturity and sound engineering principles based on practical experience mattered more than theoretical technical innovation pursued without regard to manufacturing reality. German tank designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority. They were wrong. American tank designers built reliable vehicles because they understood through hard experience that logistics, maintenance capability, and sustained operational availability determined victory in modern mechanized warfare. They were right, and their approach proved decisive. The reliability gap between Sherman and German tanks influenced not just tactical armored warfare, but fundamentally shaped broader understanding of military, industrial capacity and its decisive role in modern conflict. Germany entered World War II with technical advantages in many weapon systems, possessing scientific knowledge and engineering expertise that exceeded most opponents. However, Germany lacked the industrial depth and manufacturing sophistication to maintain those advantages through sustained mass production while simultaneously fighting enemies on multiple fronts. The United States entered the war with weapons that were less technically sophisticated in many respects, but possessed industrial capacity to manufacture them in overwhelming quantities while continuously improving quality, reliability, and performance based on combat feedback. This industrial approach, perfectly exemplified by Sherman tank design and production, proved far more effective than German technical sophistication applied to small-scale production. The United States produced nearly as many Sherman tanks as Germany produced tanks of all types combined, while also producing enormous quantities of every other weapon type, supplying allies through Lend-Lease, and maintaining the highest standard of living among all combatant nations. This economic performance, impossible to match for Germany even before strategic bombing intensified, decided the war's outcome as certainly as any battle. The mathematics were simple and brutally clear when examined objectively. A Sherman with a 75mm gun that reliably reached the battlefield and fought effectively was infinitely more valuable than a Panther with a superior gun that broke down before engaging the enemy or required 3 days of maintenance for every day of operations. A tank battalion with 80% of its vehicles operational could execute missions that a battalion with 40% operational vehicles simply could not attempt. Reliability wasn't just a convenience factor or secondary consideration. It was the foundation of operational effectiveness, determining whether armored units could execute their assigned missions. German tanks consistently failed this fundamental test throughout the war. American tanks consistently passed it. Kummersdorf testing had proven this beyond any reasonable doubt, by mid-1943. Even as German commanders continued deploying Panthers and Tigers that looked fearsome and possessed impressive specifications, but couldn't be relied upon to function when needed most. The Sherman tank didn't win World War II through technical superiority in firepower or armor protection. It prevailed through industrial dominance manifested in mechanical dependability, steady availability, and ease of upkeep. German engineers at Kummersdorf recognized this by mid-1943 through their exhaustive testing programs. They produced meticulous reports detailing their observations and verified their results repeatedly with scientific precision. They arrived at the right conclusions regarding American advantages, yet recognizing a problem and correcting it are entirely different. Challenges. German industry lacked the capacity to reorganize production around principles of reliability while simultaneously waging a losing war on multiple fronts against opponents with vastly greater resources. American industry, by contrast, had cultivated reliability within its civilian automotive sector over decades of commercial competition and merely transferred those proven methods into wartime manufacturing with remarkable effectiveness. War. Daddy 2, that single Sherman tank, captured in Tunisia and tested relentlessly at Kummersdorf for months, told the entire story through its mechanical endurance and consistent performance. Every kilometer it traveled without malfunction stood as evidence that German tank design had followed a fundamentally misguided path, emphasizing specifications over sustainability. Every test that revealed American automotive excellence confirmed that industrial maturity and practical manufacturing experience outweighed theoretical performance metrics. Each comparison between Sherman and German tank reliability demonstrated that Americans had solved problems their German counterparts had not even identified. The tank itself was ordinary in many respects, merely one among 49,000 produced. Yet what it symbolized was devastating to German confidence. Irrefutable proof that Germany had already lost the industrial war even as combat raged on, and that American productive power could never be equaled, regardless of German technical expertise or battlefield skill.